If you're like me and you've fallen down some YouTube and Netflix rabbit holes, this scene will look familiar.
A swab has been taken from the lining of one of their suitcases to indicate if they have been in contact with any illicit substances.
There are many reality shows featuring getting busted at customs. You can watch people get caught smuggling drugs in New York, in Vancouver, Auckland, Brisbane, Sydney, Rome, Toronto. Take your pick. The shows are cheap to produce, and they sit at an awkward intersection between voyeurism and law enforcement. And there's always one prop. שלום, ברוכים הבאים בעברית. הסרטון הזה עוסק במכשיר שאתם מכירים וזוכרים, אבל מה הוא בעצם עכשיו, ומה הוא יכול לגרום לבעיות, ומה הוא בכלל רדיואקטיבי. Siamo che la nonché in inchiuhulu moisisu. Le video in mailana non shini in gasi ni masi futi nimboni kanini. Kolo wenzeni ni pela. Kungani un vedala is it kinga. Futi kungani unesi balu semi sebi kungani ui radioactive.
Is something other than just tea.
It's about the size of a laser printer, and it pauses dramatically, like it's thinking, and it bleeps loudly when it detects contraband. What is this machine? Sometimes called an ion scan, itemizer. How does it work? Where does it run into problems? And why is it radioactive? During the 1960s, Erwin McDaniel, a professor of physics at Georgia Institute of Technology, Georgia Tech.
Who's got it? Georgia Tech does!
Began applying concepts first introduced at Los Alamos. McDaniel and others were exploring how chemicals behave when you turn them into gas and then give them an electrical charge. This was during the Cold War, and there was a push to identify explosives, chemical weapons, and toxic chemicals out in the field.
The bomb might explode when there are no grown-ups near. Paul and Patty know this.
The technology they produced is called Ion Mobility Spectrometry, or IMS. I'm not a nuclear physicist, so I'll do my best to explain this as well as I can.
I played a nuclear psychiatrist in a James Bond movie.
Almost everything we know is made of atoms, and atoms bond with each other to form molecules. You can put a molecule into an electrically charged gas and then test how quickly that molecule travels through it. Ion mobility spectrometry measures the speeds with which a group of chemicals can travel through a drift gas. The specific speeds can help identify what chemicals are in a sample. But why are these machines radioactive? The drift gas needs to be given an electrical charge, so IMS machines do this with beta radiation. Inside the machine is nickel-63, a radioactive isotope of nickel. It's created by adding a single neutron to stable nickel-62. This makes the nucleus inside the nickel atom unstable, carrying a bit of extra weight that it would like to shed. Nickel-63 emits low-energy beta particles, electrons. The radioactive nickel eventually decays into copper, so this technology can turn nickels into pennies. Fantastic.
This machine cannot turn lead into gold, but it can do the next best thing. It can turn gold into cottage cheese.
And if you're concerned about the amount of radiation from one of these machines, it's not quite Fukushima. It's about the equivalent of a smoke detector.
On the phone and being put on hold. Why not test your smoke alarm while you wait?
An ion mobility spectrometer heats a sample of a chemical or group of chemicals so that the constituent molecules become vapor and then launches that vapor into a drift tube filled with the electrified gas. At the end of the tube is a collector electrode. It senses when ions arrive. The question is, how long did it take for particular ions or chemicals to reach the detector. This drift time, a few milliseconds, is a chemical signature. The computer then compares these drift times, signatures, to a library of known chemicals, and if it finds a match,
Illicit substance.
but what could go wrong? On television, the machine is infallible. It appears to detect just about any drug ever, and appears to issue an indictment right there at the counter. But there's the part you don't see on television. IMS machines are temperamental. The machines are susceptible to forces like humidity and temperature. Even breathing too close to the machine's inlet can affect the results. And there's operator technique. The machine analyzes only what's on the swab. If an operator swabs the wrong spot, or doesn't touch the surface quite right, or picks up unrelated contamination, it won't work. Dogs often outperform the machines.
Now, what are you going to say if someone asks you to try drugs?
Hey, we're friends, but we won't be if you keep messing with drugs.
A trained dog's nose is still one of the most sensitive chemical detectors on Earth. But dogs are not robots. They get tired, they respond to their handlers' expectations, and they need to go out. Also, you cannot take an IMS machine for a walk. It won't accept treats, and it's really no fun at all. There are the special cases of cocaine.
Any news?
Yeah, he skipped down and went to South America.
South America? What kind of snowblower would you get us mixed up with?
Fentanyl. Cocaine is extraordinarily stable. It survives heat, humidity, and handling. Cocaine clings to surfaces and to fabrics. It transfers easily from person to person and from person to object. You don't need to snort a line of blow to test positive. You just need to have come in contact with a contaminated surface. And contaminated surfaces are everywhere. Multiple studies showed that 80 to 90% of American banknotes have cocaine residue. This is from cross-contamination in banks, bank machines, cash registers, anywhere you find cash or cocaine. And cocaine produces a strong, clean IMS signal. Ion mobility spectrometry detects cocaine easily, too easily. This means even microscopic amounts can produce a bleed. And the signal is so strong that it can suppress signals from other chemicals. What about fentanyl?
Explosion and the amount of deadly poisonous fentanyl that
If you watch reality shows, you'd think the machine would leap loudly at fentanyl. Fentanyl ionizes poorly. Its chemistry is messy. It gives a weak signal. Fentanyl absorbs ions around it, soaking them up, suppressing other chemicals and suppressing itself. Instead of producing a sharp signal, it produces a dead zone, literally and figuratively. Collect well. It sticks to oils, to plastics, to rubber, so it's harder to pick up with a swab. In other words, arguably the most dangerous, the most fatal illicit drug can go by unnoticed. IMS has two personalities, two different ways of charging molecules and of reading their drift times, one for drugs and the other for explosives. The latter is sometimes called ETD, or explosive trace detection. When ETD was first introduced, it seemed like an answer. It could thwart the threat of terrorist bombs. In 1985, bags were screened with explosive trace detection equipment as they were loaded on Air India Flight 182, a Boeing 747 from Montreal's Mirabel Airport to London Heathrow.
This is what it will sound like.
John D'Souza is a security officer for Air India. The day of the flight, he demonstrated a portable explosives detector.
The bags were screened with a PD4 sniffer, an early version of ion mobility spectrometry. The PD4 was notorious for false alarms, positive and negative. An unaccompanied bag was tagged and loaded on Flight 182, and a bomb within it exploded off the Irish coast. 329 people were killed. The ion mobility spectrometer failed to detect the explosives. In a push for technological improvements, security companies developed a trace detection portal. It looked for traces of explosives on a person rather than a bag. The passenger stepped in an enclosed booth, like a phone box or phone booth, while the machine spewed puffs of air in the passenger's face. The air was then analyzed using ion mobility spectrometry. It was a disaster. The machines were expensive, heavy, hard to calibrate. They produced false positives with astonishing frequency. The machines were often broken down and needed frequent maintenance, and not everyone is keen to step into a booth and have air sprayed at them. It wasn't just false positives. It was false negatives too. These so-called puffer machines were $160,000 each. They didn't detect a thing when a CBS reporter was sprayed with explosives and proceeded through a puffer machine at the Denver airport. After spending $30 million on the machines, the US government decommissioned them. Hence the ion scan, the itomizer, and similar devices. Smaller, less expensive, lighter, portable. They worked by testing a surface, a bag, someone's hands, a phone, computer, rather than a full-body glaucoma spray in your face.
Wonder what this feels like. Ow! That hurts! My God, is that what I've been doing to people?
Many passengers think they're being tested for drugs when they're not. It really depends on where you are at an airport or other port of entry. If it's at customs, drugs are often the target. At a security checkpoint or check-in counter, explosives are of greater interest. The technology cannot look for both drugs and explosives at the same time. The equipment has to be switched from positive ion mode for drugs to negative ion mode to detect explosives. This is a process that can take minutes to hours. When the IMS machine switches to negative ion mode, the one for explosives, everything becomes more delicate. Negative ion mode works beautifully in a laboratory. It's not so clean in real life. False positives can come from sunscreen, from hand lotion, disinfectants.
It rubs the lotion on its skin or else it gets the hose again.
False positives are constant. IMS can only say the drift time matches something in the database. It cannot say how much is present, where did it come from, is this something that's actually dangerous? So why bother with these machines at all? A real detector, like a mass spectrometer or something like that, can cost $100,000 to $500,000 each. These machines require trained chemists, calibration. Yeah, they produce fewer false positives, but far higher operating costs. An IMS unit costs $25,000 to $40,000. And these run mostly by pushing a button. IMS technology is portable and it's fast. Despite its quirks, IMS gives a result in 5 to 12 seconds. Nothing else works quite that quickly or that cheaply. And it's visible, not just on television. There's a certain amount of security theater in the quest to find drugs or explosives.
Customs and Border Protection have taken aside this Australian who has just returned home after backpacking around Thailand for 6 months.
What is this all about? Sorry? What's this all about?
A thorough bag search has not found any concealments, but a swab test of his personal belongings has tested positive for cocaine.
An IMS fits that bill. It looks serious, it looks high-tech. On television, IMS has scientific reliability. In real life, it's a temperamental detector that throws false positives, misses fentanyl entirely, and has to switch personalities if it needs to look for a different category of substance. But airports and ports of entry rely on this technology, not because it's perfect, but because it's fast, it's portable, and it's cheaper than other options. The physics and chemistry behind this technology is nothing short of amazing. But it's a tool, not an answer. If you'd like to try it out for yourself, you can purchase the machine on eBay. I'm not endorsing this. It's $1,300 US. That's if you use a coupon. That doesn't include shipping. If you're more budget sensitive, you can buy a PD-4 sniffer, the one that failed to detect the bomb on Air India Flight 182. It's available for just $281.75. That's if you use a coupon. In tragic irony, the product ships from India. Thanks so much again, and see you in the next one. תודה רבה, שוב להתראות. גיובונגה, כוחו לגן ענן. סיזון ענן.